Hey everyone, in this video we're going to be talking about spur and helical gears and specifically looking at the AGMA method for stress and strength. And this video is part of a lecture series in Mechanical Design 2. And what we're going to be doing in this whole module and a few of the parts of this module is that we're going to be learning the AGMA method for solving for stress as well as contact stress, and then how we can compare that to the strength of our gears. And this is a whole methodology that has been developed over the years and kind of replaces any other stuff that we've done so far, which would be the Lewis bending equation as well as surface durability analysis. So from now on, we're going to be using this information to move forward with our analysis, and this is a much more complete analysis. Now, in order to learn this AGMA method, one way to learn it is to go through and kind of understand every little intricacy of the method, but I think it's much more effective to actually go through an example problem and learn as we go through an example problem how to solve this method. This method is also extremely simple to follow once you understand it, but you do have to practice it in order to remember how to use it and how to do it. So I've made available a Module 2 formula sheet, which we'll use extensively for this type of analysis, and we'll start from there. So starting with some notes that are already written down for purposes of simplicity, we're going to start by just reading the problem and then looking at the equations that are associated with the problem. So we're told that a commercial enclosed gear drive, so a lot of new words here, but a commercial enclosed gear drive, so that's a type of gear drive that we have, consists of a 20-degree spur pinion having 16 teeth driving a 48-tooth gear. So we already know that we have a 16-teeth pinion with a 48-tooth gear, which we've seen before, and the pinion speed is 300 RPM, the face width is 2 inches, and the diametral pitch is 6 teeth per inch. So far, we have some information based on just geometry and rotation speed. Now, the new information here is the gears are grade 1 steel through hardened at 200 Brunel. So now we have some more information on the type of steel that we're using and how it's been through hardened. So a little bit more information than the usual information that we had so far. It's also made to number 6 quality standards. So we'll look at what that means later on as we go through this problem. Uncrowned and are to be accurately and rigidly mounted. So this is a methodology that is called accurately and rigidly mounted. It means that they're mounted in a certain methodology that can be followed according to the AGMA method. So assume a pinion life of 10 to the 8 cycles. So we're also going to take into account the life of the pinion itself and the life of our gear and pinion pair, and a reliability of 0.90. So we'll talk about all these different things. Determine the AGMA bending and contact stresses and the corresponding factors of safety if 5 horsepower is to be transmitted. So whenever you see bending and contact stresses, obviously you have two choices. You can either use the Lewis bending equation, and for contact stresses, you can use the contact equation that we derived in the last video. However, whenever you are asked to find the AGMA bending and contact stresses, you should follow the AGMA methodology, which we're going to learn right here. Now, AGMA stands for American Gear Makers Association, and it really is every gear maker essentially follows this association's standards and practices, so that everybody has kind of the same designs, and it standardizes designs over the whole industry. So this AGMA bending and contact stresses, we're going to start by looking at just bending stresses, and then we'll go into contact stresses in the next video. So to start off with, bending stress is equal to sigma is equal to WT times K0, KO, KV, KS, all multiplied. And we don't really know what these Ks are exactly yet. We recognize that there is a KV, but we'll talk about this KV a little bit because it's going to be different than the original KV that we had. Then P sub D over F times Km times Kb over J. So a lot of different terms that we don't really know what they mean, but we're going to go ahead with it. Now, in SI units, we have the similar equation with all the very similar K values, just a few different things here and there because SI units and don't really follow the AGMA method. They follow a slightly different method. So if you're using the AGMA method, you can kind of translate it to SI units as well, which would be WT, KO, KB, KS, I over B times MT, and all the terms are going to be defined under times KH, KB, and then YJ. Now, just to name all the terms within these equations, and these equations are also available in your Module 2 formula sheet, so I'll go to your Module 2 formula sheet after to show you where the equations are. But we have WT is equal to transmitted load. Then we have PD is the diametral pitch. It's P sub D just because that's the standard they use in this equation, but you can just use P as well, but it's essentially just a diametral pitch. F is the face width, which in SI units is going to be little b. Then J is a geometry factor from bending, which we'll talk about. M sub T is the module. So instead of M, it's just M sub T, but it's the same thing, and it's only in the SI unit version. And then KO is the overload factor for non-uniform loading. KV is the dynamic factor. And I've highlighted this dynamic factor because it's different than the Lewis bending dynamic factor. So we can't use the same KV calculations for the AGMA method. KS is equal to the size factor. Then Km or Kh in SI units is a load distribution factor. And then Kb is the rim thickness factor, which we'll go through one by one essentially. Now, in this part of the videos and in this course specifically, we're only going to use US units moving forward. So we'll only do some US units problems, but you can definitely do some SI unit problems as practice if you want to as well. Okay, so moving forward from this, we can take our problem and we can start solving our problem step by step. And what we're going to do is we're essentially going to write the equation down. So I'm going to copy and paste this equation really quickly. And we're going to start looking at this equation based on the problem. We're going to start solving the problem step by step and term by term, essentially. So the first term is our WT, and hopefully we already know how to solve for WT. So let's start with WT. And to solve for WT, we know we're going to have US units because our problem gives us our units in US units. So we have WT is equal to 33,000 times H over V. And we know that H is equal to 5 horsepower. We also know that we have to find velocity, and velocity is pi dn over 12 in US units. In order to find the diameter, we know that 5 horsepower is being transmitted through the pinion. So we can find the diameter of the pinion. And the diameter of the pinion would be 16 teeth divided by 6 teeth per inch. Okay. And so we get that we have 2.667 inches for our diameter of the pinion. Then, based on that, we can find our velocity. We can say it's pi times 2.667 multiplied by 300 RPM given in the problem, all divided by 12. And we get a value of 209.4 feet per minute, or FPM. Okay, then from there, we can then solve for WT, and we can say that WT is equal to 33,000 multiplied by 5 and divided by 209.4, and we get a final value for WT of 787.8 pound force. Okay, so that solves our first term in the equation that we had to find based on the problem. Now, the next term we need to solve for is a new term, and it's called the overload factor. So the next term is going to be the overload factor. So we're going to solve for this overload factor, and we're going to try and understand what this overload factor means. Okay, so we're going to go back to a little bit of theory and kind of define what this overload factor means. So the overload factor is and accounts for additional loading due to variations in load. So depending on what type of application you have, you could have a pinion speed of 300 RPM and your whole operation could happen at 1 RPM. But if you think of, for example, a car gearbox, you will always have changing RPM for your pinions and gears. And when you have these changes in RPM, you're actually creating these overloads of additional loading when you're accelerating and reduced loading when you're decelerating. So this overload factor takes that into account. Basically, whenever you feel shock in operation or something is happening, we typically have different values for this overload factor, but usually within the scope of most machine gearboxes and gearboxes used in industry for any application of machines and stuff like that, we're going to usually assume that we have an overload factor of 1 because usually it is neglected due to the fact that we don't have huge variations in loads. So usually we're going to say that it is neglected. And for the purposes of this, lecture series as well as this class in general, we're going to assume that KO is always going to be equal to 1 unless we're given a different value. Now, I want to take us to the Module 2 formula sheet to try and look at the formula sheet at the same time and understand where we can find this overload factor if we're ever doing a problem and we don't know where to look. One way to go to is to go to your textbook, and find your overload factor, which would be in Shigley's Mechanical Design. Another way is to go to the Module 2 formula sheet. And in the Module 2 formula sheet, first of all, I want to show you the AGMA bending equation. So the equation that we just wrote out is right here. So we have the AGMA bending equation, which is here, available for us to copy over whenever we need to do a problem. And you'll see that all the terms in the AGMA bending equation are shown on the left side of this formula sheet. So we have a bunch of different factors that we'll talk about as we go along, but we can go look for our overload factor, or KO. So here we have our KO, which is defined as our overload factor, and we can see that for uniform loading, KO is going to be equal to 1. And that's what's given in this formula sheet. So whenever you're doing a problem or trying to work on a problem associated with this, if you're doing it with uniform loading, you should say KO is equal to 1. If you don't know what type of loading there is and it doesn't tell you in the problem, then you would just have to assume something. So in this case, we're going to assume that there is uniform loading because the RPM is pretty much constant within our system. Okay, so we're good to go with that. So just to show you where it is in the formula sheet itself. Okay, so we have KO is equal to 1, therefore let's add a check mark, and I'll add some check marks as we go. So KO is checked for. We're going to assume that KO is equal to 1 in this specific problem. Okay, so then moving forward, we have the next term is KV. So we're going to point at KV just so we follow the same technique as before. So we have KV, and we're going to define KV and work on KV. Now, first things first, KV is not the same KV that you use in the past. So it is different, and you can't use the one for Lewis bending or surface durability. So it is going to be different. And it is also going to be called the dynamic factor. And you can kind of define, like, call it the AGMA dynamic factor, just so you don't get confused. And on the left side of your formula sheet, this dynamic factor will be calculated um, from that left side of the formula sheet. So the formula sheet doesn't have any other information on the KV for Lewis bending and surface durability. That would be in your handout. Okay. All right. So this dynamic factor, what are we talking about? Well, what we're talking about is this dynamic factor is created uh, because what happens is we usually have a departure from uniform loading due to inaccuracies in manufacturing. So it's not really what we were thinking of when we were thinking of the dynamic factor, and the fact that at speed there could be a change in the dynamics of everything that's happening. In this case, we typically look at the dynamic factor and say that because there are changes in velocity and the velocity is higher than, because of the increase in velocity, we can have some problems with uniform loading that occur because of inaccuracies in manufacturing. So that means that if you have a better manufacturing technique, you might have a lower KV factor even at the same speed. Okay, so that's something that we need to take into account. And for this to be solved, we're going to need a few different quantities. And we're going to look at the equations in our formula sheet first, and then I'll copy them over after the fact so that we can see what's happening. So going to our formula sheet, we can see that KV is given to us in this part right here. Okay, so we have KV right here. Okay, so this whole section is for KV. Okay, and we see that we have a few different equations. We have an equation that says B, an equation that says A, and then we're seeing that KV is equal to A plus the square root of V divided by A all to the power of B. And we also have a term that says or C chart. Okay, so we're going to be able to use a chart in order to simplify our KV calculation. Now, obviously, if you're under a time constraint, you could use a chart. However, using the equation would make more sense in order to get a better value in terms of your final result for KV. So regardless of the material, you can use this A equation and B equation to solve for KV. So I'm going to write it out into our notes so that we have it in our notes, and then we'll look at the chart after we've calculated. So let's start with first calculating it by hand using the different terms that we need. So we can say that we need, the different things that we need are A, B, and Q sub V. Okay, now Q sub V is a term that we haven't introduced yet, but is called the quality. Okay, and we're told in the question, if we jump back to the question, we're told that the gears are grade 1 steel through hardened at 200 Bernal made to number 6 quality standards. So these number 6 quality standards are a set of standards set forth by AGMA, and you can follow those quality standards in terms of tolerances, in terms of all the different ways to manufacture. And you know that in this system, it's made to number 6 quality. So we can say that the quality is going to be equal to 6. Okay, we're just going to use a number for the quality. Then we can write the equation for B and the equation for A. So I'm going to write the equation for B first because B includes QV into the equation, and A then needs calls for B. So B is equal to 0.25 times 12 minus QV to the power of 2/3. And if we solve with QV is equal to, I'll write V a little bit better, QV is equal to 6, you get that this is equal to 0.8255. Okay, then we can solve for A. A is equal to 50 plus 56 multiplied by 1 minus b. So we're going to plug in b here, 0.8255, which is going to be equal to 59.77. Okay, then we're going to recall from our pitch line velocity that our pitch line velocity is equal to 209.4 feet per minute. And we're going to be able to plug into our kV equation now that we have all the terms. And we know that kV is equal to A plus the square root of V over A, all to the power of B. And if we actually plug into this, we get 1.196. Okay, so that would be the value that we get for kV. So now we're done. We have kV and we're good to go. Okay, so I'm going to check off that we have kV. Now, before we move on to the next one, I want to show you how to use a chart as well. So we have a chart that's available. So if we use the chart, so I'm going to have like an alternative method, we can say that, especially if you're under time constraint, this alternative method is good. So we can say that from chart, kV is equal to, let's go find out. So let's go back to our formula sheet. Okay, our formula sheet is going to appear here. And we're going to have different graphs that we're looking for. So we're looking for a graph with kV. So on the first page, we don't have any kV, so let's go to the second page. And in the second page, we see that this chart right here has a dynamic factor kV versus pitch line velocity. Okay, and we also see that there's different qualities that are like different lines for qualities. So we have QV equals 5, QV equals 6. So the quality is typically usually between 5 and 11. And then there's another step even higher, which is called very accurate gearing, which is higher than 11, essentially. It's a quality that is higher than the standard of quality of 11, but typically it's going to be anywhere from 5 to 11. So we can see when we have a quality of 6, we're actually looking at a system where the kV value is going to be a little bit higher, which is going to increase our stress. If we look at kV compared to stress, it's on the top of the equation on the right side. So if you increase kV, you're going to increase your bending stress as well. Okay, so QV being higher helps with kV lowering, essentially. Okay, so it's a good visual representation of how kV is calculated based on quality. Now, the other thing we need to know is our pitch line velocity in feet per minute. So we already have our pitch line velocity. So if we looked on the graph here, and I'll highlight in red, we can say that 200 is around 10% of the initial gearing. And then if you go up, and 10% is a little bit closer to the left probably, it's a little bit hard to tell, obviously. But if you go up, you would get somewhere along the lines of, and let me try and zoom in a little bit here so you can see a little bit better, but you would get that the value would be around 1.2. Okay, so you can see how it would be probably more effective to use the equation, but if you use the graph, you would actually get a kV of around 1.2. And I'm going to put that this is an estimate. Okay, so if we look at the graph itself, I'm going to put that this is approximately equal to 1.2 from chart. Okay, so that's another alternative method to find kV. So it's up to you whether or not you want to use one or the other, but it's completely fine to use one or the other. Okay, so moving forward, we then have to look for the next factor, which is Ks. So let's look at Ks next. Okay, so Ks is called the size factor. And in the same way as the other factors, it's a corrective factor that we use compared to WT, essentially. So this is, the size factor is the reflection, or the reason this factor exists is the reflection of non-uniformity of material properties due to size. So obviously, depending on the size of our system, our material is always going to have the same particles spreading, whether or not the gear is 1 inch wide or the gear is 100 inches wide. So definitely there could be some problems with materials properties due to size. Now, some designers just forego this completely and say some people assume negligible. So some people say that KS is just equal to 1. Now, if you're ever in a situation where you would take an exam on this, you would definitely use KS is equal to 1. And I've reflected that in your formula sheet as well. So if you go to your formula sheet, if you go to your Module 2 formula sheet, I'm still going to teach you how to find KS. But if you go to the formula sheet on the first page of the formula sheet, we see that KS, the size factor, is just equal to 1. Okay, so it's shown right here. KS is just equal to 1. So you can use KS is equal to 1 unless otherwise noted. Okay, so now in order to find the size factor, in this case, because we're doing an example problem, we actually want to calculate what the size factor would be. We're going to write the size factor as the following. We're going to say that KS is equal to 1.192 times F square root of Y over P. Okay, and this is going to be to the power of 0.0535. So not a simple equation to go with, but if you do remember this equation, you can use it. And then based on that, you could find a KS for your system. Now, what is P in this equation? P is diametral pitch. So we have that F is the face width, and then Y is actually our Lewis bending factor. Okay, so that means we have F is equal to 2 inches from our problem. We have P is equal to 1/16 per inch. And then we have a Y value, and we're going to have 2 different Y values in our problems. That means that we're also diverting between the 2 systems that we have. So whenever we're finding sigma for bending, okay, so let's put a sigma sum bending, we're going to find the sigma bending for the pinion and for the gear. And they're actually going to be different, okay? In most cases, they're going to be different because the pinion and gear have different number of teeth, okay? And this is the first term where they would actually differ slightly. And there's other terms that we'll look at that are also different. So Y of 16 and Y of 48, we can go to our formula sheet to go find out these values. So if we go to the formula sheet on the bottom right of the formula sheet, we have that Y for 16 is equal to 0.296, and then Y for 48 is going to be an interpolation between 43 and 50, which is going to come to 4056. Okay, so we're going to write those down. We're going to say that Y16 is equal to 0.296, and Y of 48 is equal to 0.4056. And that means that we can then calculate our KS, but we're going to have a KS for our pinion and a KS for our gear. So the KS for our pinion is going to be equal to 1.088, and the KS for our gear is going to be equal to 1.097. Okay. The next term we're going to look at in all the terms that are K values. So I'm going to check that we have our size factor now. Again, if you're doing an exam or something with time pressure, you could just write that KS is equal to 1. Then we have PD, we have F in the problem. So the next thing we need to look for is KM. Okay, so the next term we need to look for is KM. So let's solve for KM. And you can see that this approach is becoming very systematic, okay? So it makes it pretty systematic and pretty easy to solve for. So this is called the load distribution factor. okay? And the load distribution factor takes into account if you have non-uniform loads, okay? And this is, the following equation is used for this. So Km is equal to 1 plus CMC times CPF times CPM plus CMA times CE. Okay, and we can see that that's a pretty complex kind of equation to follow to be able to solve for this problem. Now, one thing we're going to be doing here is we're going to be defining this mesh alignment factor, but the easiest way to solve for this is to actually look at our formula sheet. So because there are so many terms, we want to look at our formula sheet and kind of solve term by term and see what's happening. Okay, so we're going to see formula sheet based on the information we have. And for this term, we're also going to be using, we're also going to be finding Km just for the pinion, okay? So we're going to be finding Km for the pinion and using that for both pinion and gear. So because it takes into account the two gears together, we're going to be looking at the load distribution factor for pinion, but used for both sigma for pinion and sigma for gear, okay? So that's a little bit of a rule that we have to follow. We're using that value for the pinion and gear. Okay, so let's go into our formula sheet and try and understand what's happening here. So if we go to the formula sheet and we go back to the first page of the formula sheet, we have that, and I'm going to erase some of the annotations here so that we have some space and clarity. Okay, so we have Km, the load distribution factor, which is drawn right here. And we're told that we have to follow all these different terms, okay? So we first have to find, so we see that Km is equal to CMF, which is equal to 1 plus CMC times all these different terms. So if we have uncrowned teeth, we have CMC is equal to 1 for uncrowned teeth. Now, most of the time we are going to have uncrowned teeth. Now, then the next thing that we need to find is CPF. CPF is a different equation based on different face widths. So for the face width that we're looking for, we're going to find CPF this way. So we're going to use this equation to find CPF in our case. Okay, then CPM is going to be equal to 1, so we have CPM. CMA I'll get back to. Then we have C is also equal to 1, so we can use C is equal to 1. And then the last term that we need to solve for is our CMA, okay? So CMA, we have to C chart, okay? So a couple of things, first of all, is we have to go see the chart. So we have to go find a chart with CMA, okay? And our CMA is going to be shown here. We have our mesh alignment factor, okay, which is CMA, versus our face width, okay? So, well, we know our face width is 2 inches, and we're also told that we have a commercial enclosed gear unit. So if we know that we have 2 inches in a commercial gear enclosed unit, we have that the value is going to be right here. Now, another thing you can do is use equation 14.34, which is in Shigley's mechanical design book. However, we're going to simplify the problem and always use the chart, even if it's not the most accurate methodology. And we can write that CMA, based on the chart, is equal to 0.60. So going from there and going back to our notes, we're going to write the following thing. We're going to say that CMA is called the mesh alignment factor, It's the only one that we really need to look for in terms of a chart. And we found that CMA is equal to 0.16. Then from our notes in our formula sheet, we have that CMC is equal to 1, CPM is equal to 1, then CE is also equal to 1, and we're left with finding CPF, which is one of the three equations, but we use the equation between 1 and 17 inches, which is F over 10D minus 0.0375 plus 0.125F. And what we're going to use is we're going to use the diameter for the pinion here. Okay, remember we're solving this for the pinion, but using it for both. And we're going to write that Km is equal to 1.2225. Okay, so moving forward from here, we then have to find the next term. So we have Km is equal to 1.2225. The next term that we're going to look for is our KB value. So if we go back to our original equation, we're going to write that we found Km and we're left with KB and then J. So let's find KB first. So KB is called the rim thickness factor. And what it takes into account is whether or not the gear rim is thick enough for prevention of fatigue cracks. So what do we mean by the rim thickness? So I'm going to write a few different things here. So we're going to write that if MB is greater than 1.2, so this MB value should always be greater than, hopefully should be greater than 1.2. We can say that KB is going to be equal to 1. Okay? And what this MB is the ratio between T sub R and H sub T. And obviously that doesn't mean anything to us yet, but essentially T sub R is the rim thickness and H sub T is the height of the tooth. So if I were to draw a gear set, we typically don't have gears that are fully full metal with some teeth on top. Okay, that's not usually how it happens. So this is not all filled. What we usually have is a gear that has a certain rim thickness. So if we zoom into the top part of a gear, our gear is going to look something more like this, where we have some teeth, and I'm just drawing two teeth for information purposes. There's more teeth, and we go like this. Okay, there's more teeth around, but I'm just showing you what happens. So the distance from here to here is our T sub R, okay, which is our rim thickness. And then the distance from here to here is our H sub T, which is the height of the tooth. So if T sub R is 1.2 times greater than the height of the tooth, we don't have any problems, and KB is equal to 1. So essentially, in most cases, KB is going to be equal to 1 due to that rule that we have. Now, it doesn't tell us in the problem whether or not we have that ratio or not, but we can assume that. So this is an assumption that we have to make. So we have to assume, if not given, that KB is equal to 1. So we can see that there's a lot of these terms, but a lot of these terms actually simplify to 1. But we need to know about them because in case we're actually designing real gearbox systems, we might have a problem and we might have to take that into account. So going back to our formula sheet, if we go really quick to our formula sheet just to look at it on the first page, we can see that if we go look for KB, and KB here is with a capital B, is going to be equal to 1. Okay, so the rim thickness factor is going to be equal to 1, and it's always going to be equal to 1 according to our formula sheet. So we can just say KB is equal to 1. Okay, one last term to find. So we can say that we found KB already. So we can plug for that. We can write for that. And the last term is our J term. Okay, and I'm not going to check the J term at the end because we're going to have it, but then we'll solve the problem for the actual number. So J is another one of those terms where we're going to have two different things. So J is called the geometry factor. Okay, so we have the geometry factor, and it's going to be split into two parts. So we're going to have a pinion and a gear answer. So this is another term that is split between pinion and gear. And what I would suggest is when you're working on this, you should write that you're going to have a J sub P and a J sub G, just like you would have a KSP and a KSG. Now, if you assume KS is equal to 1, then you don't have to find KSP and KSG. But if you do have to find it, then these are the two ways to find it. Now, what we're going to do is we're going to use the chart to find the geometry factor. So we don't really have an equation associated with the geometry factor, so we're going to use a chart. And we're going to go to the chart and try and figure out from the chart what the values would be for J. Okay, so the chart for J is on the second page at the top. And we can see that this is a little bit of a more complicated graph because we have a few different things. So we have the geometry factor value on the left, and then on the bottom is the number of teeth for which a geometry factor is required. So this is, for example, 16 teeth if we're looking at the pinion, and 48 teeth if we're looking at the gear. Now, here on the right side, it says load applied at the highest point of single tooth contact. And it gives us the number of teeth in mating gear. So we're going to have to find two geometry factors. One with essentially 16 here and 48 here. And another one, I'll draw it in blue, with 48 here and 16 here. Okay? Now, if we're told that the load is applied at the tip of the tooth, then we would use a geometry factor on the bottom line, but that's usually not the case. It would be the case if we're assuming Lou is bending, for example, but in most cases, we're not going to assume that. So let's start with the red line first. So we're going to be looking at the number of teeth for which geometry factor is desired. So we're looking for J sub P, or J for the pinion, and we have conveniently that 16 teeth is here, and we're meshing with 48, but we see that when we have 16 teeth at the bottom, we only have one line for all the different teeth numbers at the top. So it actually makes it a little bit easier for us to solve for. We just have to find this value and plug this value in. So we can see that JP is equal to 0.27. Now that I go to blue, I'm going to do 48 versus 16. So if I have 48 versus 16, I'm going to go somewhere here at the bottom between 45 and 50. And I'm going to go all the way up to 17. And I know I'm going to be a little bit lower than that probably if I extrapolate. Okay, I can see that the gap between 25 and 17 is a value. So I'm going to go a little bit down. And I'm going to be anywhere in between 0.38 and 0.39. So I'm going to use, just to make sure that we don't have the same value as for 17, I'm going to use JG is equal to 0.38. Now, JG might be 0.385, 0.39. It's completely fine if you use 0.385 or 0.39 as well. Okay? And now that we have the values, what we can do is we can start plugging into our sigma, we can finally solve for sigma. So our sigma values, going back to our notes, I'm going to write the JP value, so 0.27 and 0.38. And I'm going then to be able to solve for my bending stress. So we're going to have a sigma, and usually we put a bracket with P and then a sigma for the gear. We have two different sigmas because we saw that KS are different and our JP and JG are different. So based on that, we're going to write that sigma P is 787.8 multiplied by 1 multiplied by 1.196. So I'm just plugging in the numbers one by one, multiplied by 1.088, multiplied by 6 over 2, that's P over F, multiplied by 1.2225 times 1, all divided by 0.27. And I get a value for sigma P of 13,924 psi. If I do the same thing for sigma G, but I replace our KS and our J, then I would get a value for sigma G of 9,975 psi. Okay, so those are the bending stresses that the pinion and gear encounter in the whenever they're in contact with each other, given the parameters in our problem. So looking back at our problem, we can say that now we've determined the AGMA bending stress. So we've done essentially this part of the problem. We've done the AGMA bending stress. We're still missing this part, and we're still missing the factors of safety, which we'll talk about later. Okay, so what we're going to do is in the next video, we're going to solve for the contact stresses. And then in the video after that, we're going to solve for the factors of safety. Okay, so we'll see you in the next video for this, but hopefully this all makes sense. And again, if there's any questions, you can leave them in the comment section or you can discuss them as part of the class. Thank you.